All right, EV4 has what is probably our hardest or most challenging vector equation to write. Again, just like in EV2, when we're talking about spanning sets, we're given a set of vectors. And so setting up an equation means we not only have to put the linear combination of these vectors, but we need to know what that result vector should look like. What is the solution to this linear combination? So let's just start by labeling each of these vectors so we don't have to rewrite them because we can be lazy. And we'll put in our linear combination. Now, when we're talking about linearly independent, the smartest place to go with this is to use our zero vector. And with our zero vector here, if these are linearly independent, first off, we need this system, the corresponding system of equations, or this vector equation, to be consistent. There has to be a solution. That's important. But we also know that we can't have infinite solutions. If there's infinite solutions, then we're in trouble because that means one of our vectors was a linear combination of the others. And so we need this to have exactly one solution. And that solution, if you want to be cute about this, that is the solution where all of my scalar multiples must have been 0. So that is how we're supposed to figure out, or how we're supposed to write out this statement about the solution to a vector equation if we want to show vectors are linearly independent. There are maybe other ways around this, depending on the situation. In this case, since we have 3 vectors in R4, this was the only correct way to write this statement. And the second part asked us to look at the reduced echelon form matrix based on those vectors as columns, and then asked if we could determine if the vectors are linearly independent or not. And in this case, we can see the answer. So the answer here is no. The vectors are not linearly independent. So you could definitely write linearly dependent. And then a reason why we could see that. Now here we have because there are 2 pivots in the 3 columns, right? That's one way we could look at this, because now we're comparing pivots to columns versus pivots to rows, like we were when we were talking about spanning. We could talk about because there is a non-pivot row, or non-pivot, sorry, column, third one, meaning we can write V3, as a linear combination of V1 and V2, right? So yeah, we have lots of different ways we could get to this, but something along the lines of referencing this column here, the fact that we don't have a 1, we don't have a pivot there in this position, or even the last position, is telling us that we are in trouble here, and that we could actually write this column as, oh, it looks like it's definitely a -2 times this first one, right? And then a negative of the next one too. So that's where we would have had to go. But anyways, again, so if I wanted to write that out, V3 is equal to -2 V2 minus V1. But anyways, that's what you were looking for, something there. If you talked again about pivots to rows, that's about span, so you wouldn't have gotten full credit on this. If you talked about 2 pivots and the fact that we're in R4, again, that's about span. We needed to talk about the columns, or the number of vectors. Our number of pivots has to equal our number of columns, or has to equal our number of vectors for this to be true. You could also have gotten there, though, of course, by talking about the non-pivot column, because that non-pivot column is causing some troubles for us.